All right, so now we're going to talk about binary numbers and errors. So basically, we're going to discuss how computers represent numbers and the potential sources of error. It's like which arise it's like due to the way the computer chooses or to represent numbers. Okay, so these are binary numbers and errors. Okay, so in particular, how computers represent numbers. So the computer representation. Okay, so most of the numbers we work with, it's like are in base 10. So we usually think in base 10, sort of decimals. Okay, so if you have a number, say 523.61 in base 10, you should really think of this as being 5 times 10 to the second power plus 2 times 10 to the first power plus 3 times 10 to the 0th power plus 6 times 10 to the minus 1 power, and then plus 1 times 10 to the minus 2 power. Okay, so the digit to the left of the decimal point, right, is the thing which has the base to the 0th power, right? And then as you keep moving left, it's like you increment the power by 1, and if you move right, you decrement the power by 1 each time. Okay, so by analogy to this, right, so computers represent numbers in base 2 because of the fact that they represent it as an on or off state. Okay, so so each bit, it's like each unit of storage it's like in a computer can represent a state. It's like as either being on or off, or 0, 1. Okay, so the computer stores numbers in base 2 or binary. Okay, so all right, so for base 10, it's like every digit goes from 0 up to 10 minus 1, which is 9. So in base 2, every digit goes from 0 to 2 minus 1, which is 1. So it's either 0 or 1 for each position. So for example, you have 101.11 in base 2, right? So that's equal to 1 times 2 squared plus 0 times 2 to the 1 plus 1 times 2 to the 0 plus 1 times 2 to, 1 times 2 to the minus 1 plus 1 times 2 to the minus 2. Okay? All right, so that's how you represent numbers. So let's look at how we go from binary to decimal. Okay, so let's say, let's look at a few examples, right? So 11010 in base 2, right? Again, let's maybe it's like start from this end. So 0 times 2 to the 0 plus 1 times 2 to the 1 plus 0 times 2 to the 2 plus 1 times 2 to the third power plus 1 times 2 to the fourth power. So that's, okay, so that's 2 plus 8 plus 16. Okay, so that's 26 in base 10. Okay, and then you can do another example, say 110.11 0.0101 base 2. Again, okay, so this is 1 times 2 squared plus 1 times 2 to the 1 plus 0 times 2 to the 0 plus 1 times 2 to the minus 2 plus 1 times 2 to the minus 4. So that's going to be 6.3125 base 10. Okay. All right. All right. So that's sort of fairly straightforward. So let's look at the reverse from decimal to binary. Okay. So I'm first going to talk about how do you convert the integer part. So conversion from decimal to binary. Okay, so the first part I'm just going to look at the integer component. Okay, so let's say we have an minus 1, a1, a0 base 2 is equal to some number x in base 10. Okay, so that means that, so this is going to be an 2 to the n all the way down to a0 2 to the 0 is equal to x. Okay, so let's say x is 26 in base 10. Okay, so what you do is you keep dividing by 2 and then looking at the remainder for each of the terms. And then right. So if you think about this thing here, if you divide this by 2 and look at the remainder is going to give you a 0. Okay. And then you sort of keep doing that. You divide by 2, it's like, and look at the remainder, and then it will keep giving you the digits in that expansion. So if you look at 26 and you divide by 2, you know you get 13, and there's no remainder, so that means that a0 is 0. That makes sense, right? Because you know that if you look at this expansion, all the other terms are going to be even. The only possibly odd term is coming from a0 here. Okay, so 26 is even, right? So you don't expect to see a non-zero coefficient for a0. Okay, so 13 is odd, right? So you expect a1 to be 1. So 13 divided by 2 is 6 with a remainder of 1, right? So 6, you divide by 2, that's 3, right? Okay, so this a2 is 0 because 6 is even, right? 3 is odd, so a3 is 1. 3 divided by 2 is 1 with a remainder of 1, and then that's a4 is equal to 1. Okay, so what that tells you then is that 26 in base 10 is equal to 11010 in base 2. 11010 in base 2. Okay, and again, if you would like to work backwards, right, so you can check that this is equal to 2, sorry, 1 times 2 to the 4 plus 1 times 2 to the 3 plus 1 times 2 to the 1. So it's 16 plus 8 plus 2 as before, which is 26. Right. Okay, anyhow. All right, so this is how you go back and forth between this. That's the integer part. Now let's look at the fractional component. Okay, so there's a point there, a1, a2, a3, and so on. Base 2 is equal to x in base 10. Okay, and then we have a1 times 2 to the minus 1 plus a2 times 2 to the minus 2, and so on, is equal to x. Okay, so what you do is to multiply by 2 each time, and if you multiply this by 2, right, then you, if a1 is 1, right, you will have a integer part of it, right, and if a1 is 0, it's like then you don't have an integer part. Okay, so that's sort of the idea. Okay, so if you have, okay, let's look at an example. Right, so if x is, say, 0.3125 in base 10, right, then you take 0.3125 and you multiply by 2. That is 0.625. Okay, so there's no 1 here, so a0 is 0. Sorry, a1 here is 0. Okay, you have 0.625 and you multiply by 2, you get a 1.25. So a2 is 1, and then you just take the fractional part of that, which is 0.25 times 2, you get 0.5. So a3 is 0, and then 0.5 times 2 is 1.0, and a4 is 1, sorry. And then if you just take the fractional part of that, that's 0, so that ends. So you know that 0.3125 in base 10 is equal to 0.0101 in base 2. Sorry, 0.3125 in base 10 is 0.0101 in base 2. Okay, and then of course you can combine, it's like the integer part, which we discussed, and the fractional part, which we discussed, to convert any sort of generic sort of decimal, it's like into its binary equivalent. Okay, so what's going to happen basically is that you know, most computers only represent numbers with a finite number of digits, if you will, right, binary digits. And so what's going to happen basically is that you know, you're going to end up introducing some sort of discrete number system. It's like on the computer, it's like, so it's only able to represent a finite collection, it's like, of numbers, and the number which you're working with has to be represented in that. And if the number you're working with is not exactly representable in your computer number system, then you introduce an error there. Okay, the danger, if you will, is that when you then take these computer representations of numbers and you start manipulating them, like if you add two numbers together, you divide by them, that representing the result of that operation, again, it's like in this number system, can introduce additional errors, which we call round-off errors. Okay, so let me sort of just briefly talk about some examples of errors, and then in the next lecture we'll go into greater detail on some of them. Okay, so there are several sources of errors. Okay, so the first of which is, if you go back to this sort of diagram, it's like which we introduced at the start of the class. It's like where we talk about the process of taking a real-world problem and then replacing it with a model. The first source of error, as you might expect, is what is called the modeling error. The next source of error is the discretization or truncation error. And we saw an example of truncation errors where, for example, you take a continuous function with some regularity and you replace it by some finite Taylor series approximation of it. All right, so you don't take the infinite Taylor series, you just take some sort of finite Taylor polynomial, and by discarding the rest, it's like you've introduced some sort of truncation error. Okay, the third thing is this idea of round-off error. And round-off error is associated with the fact, as we've discussed briefly, that when you represent numbers on a computer, you typically can't represent all possible numbers, and there is a sense in which you have to project your number onto the set of numbers which can be represented in the computer. And when you start manipulating numbers on the computer, you again have to reproject that answer back into this space. And each time you do that, you can introduce an error, which we refer to as round-off. Okay. The fourth thing is you could have error in your data. And then the fifth thing is human error. So we're primarily, again, going to focus on these middle three sources of error and then try to understand, what happens when when you have this kind of error. So as an example of data error, it's like you might have that the parameters which you've written down are slightly incorrect, and you have to ask yourself, well, if I take this mathematical problem and I were to change the numbers slightly, does my answer only change by a small amount, or does it change by a big amount? All right, and so that's something which is useful to know. It's about your numerical method. Do small changes in the data result in small or large changes in the numerical answer which you get. So again, we're going to focus on 2 to 4 and during this class. Okay, so let me just stop here for now.